is our our secretary. She has that thing, prestige. Ah, yeah.
Yes, so Dani,
We'll start?
yeah.
So, hi everyone. Happy Pi Day, the actual Pi Day. And pi is meant for irrational. So we have started with lots of irrationalities today. So the day can't be better than this, I guess. And we have another Bhatnagar awardee for our celebrations. And I'm so honored to introduce Professor Gadadhar Mishra. He's a great leader, he's a great mentor, and all of us used to love him so much. He's student friendly, and he's a great chairperson as well. So you should interact with him beyond what is going to be happening over here. You will learn a lot of lessons, and of course you will hear a lot of stories from him. He's famous for many things, not just operator theory and functional analysis. And as he just said, he's not going to talk about epsilon deltas right now. And so let's start with an out-of-norm talk for the second day. And I hope you all enjoy the magic in the math and the fun in the math. I request Prasenjit Mandal to give a short momentum for Professor Gadadhar Mishra.
After this, you can add
Yes. What did you say?
I want it.
What is the thing?
This little place is
So, his native place is just 25 kilometers from here. So all the more reason I hope this moment
Well, thank you very much. Yeah.
And guys, I also want to add that Professor Gadadhar Mishra is somewhere from nearby, 25-30 kilometers from here, a place called, I think, Digapandi.
Digapandi, yeah.
So
That's
he is a local person.
Yeah.
Okay, sir, welcome.
Yeah, thank you. Being a mathematician, but it's very clear that you will never be good for anything else. This was the statement that was made when I was a MSc student. Now, after 35 years, I think it has come true in the sense that I haven't been able to do math. So after 35 years of having to fool around, now I have an or who knows what else. There will be a lot of do a few things. These will be hands-on in the sense that, of course, you must have heard many times that you do math by taking a pencil and a paper. I'm going to do exactly the opposite. Actually, some 3-4 years ago, I was asked to give a talk at some CSI or function or something, where I was told that you are not allowed to write an equation. What kind of younger people to think about mathematics? I mean, I don't know too many things that will make you feel math is interesting, but you don't see. So let me begin with something. As I said, I am practicing, okay? Hopefully half the time I will succeed. The other half is something where we don't care about real life applications, this, that and the other. When I say we, not everybody, but some of us take the point of view that, look, who cares what happens in the real world? We do math partly because we want to run away from the real world, okay? So the real world, believe me, is pretty difficult to take. So some of us try to do math. The picture frame that you presented right now. So you hang a picture frame on the wall. Now you can see if I move one of these nails, it still hangs, okay? I remove this, it still hangs. Now only a mathematician can think of a problem The statement of the problem is, you remove one of the nails from where your frame is hanging and the whole frame falls down. Now you might ask, the whole thing falls. Frame. Well, 29. Okay. Now let's see. So in any such magic game, you can't be doing it without one. So I need at least one volunteer now. Let me count this first of all. Not bad. So I survived this. I want to now play, as I said, I'll explain, if you are still patient, before lunch I'll tell you how all of this really works. But now I want to play a slightly different game. Yeah, that can be. So now I need 2 volunteers. This is a political game, if you like. I want to convey a political message. Let's see. I'll tell you what the rules are. I need a third volunteer. Who had come here and then? Yeah. No, you can sit there, take a piece of paper. It won't be epsilon delta, I assure you, but I want you to keep score. Alright, here is how the game is played. There are these bunch of things, right? And what you do, let me just as a demonstration tell you what you do. You divide this bunch into things like this. You are keeping the score, right? So when this gets divided like this, it is 3 and 5. So the score becomes 15. 3 times, when it's split into 2 piles, it is 15. Now suppose I do it 3, 2, next step, it is 6. 15 plus 6. This is 3, that is 2. If I do this one into 1, 1, then it's 1 times 1 and therefore 1. Add, I want to see that number. So we had what? 15 plus 6 and then 1. Plus 1. Now I do this into this. So that is 2 times 1. So that is 2. This one I do 2 times 1. That is again 2. Now what is left is this pile of 2. I make it into 1, 1. It's 1. Please add. And then this pile of 2, I make 1, 1. So that is another 1. What is the total? 28. Okay. Now let's play the game. Your job as 2 teams is the following. You want to play this game as long as your pile does not become a single block. Okay? When it becomes single block, you cannot split, so game ends. At that point, whoever has whatever many points, suppose he has 31 points and you have 72 points, then you win. Okay? Game stops when there is nothing more to divide. Okay? And at that point, we look at the score and decide who wins. Alright? Huh?
Says that before it becomes single, we will stop.
No. When it becomes single, you stop. Okay? Until it becomes single, you continue playing. So it's a game of strategy in the sense that you want to think of what are all possible different ways in which you can do this splitting so that your points become maximum. Right? You understand?
Yes.
So you keep, yeah, one step at a time, so you split. So now 4 times 4, you make 2 columns, okay? So C gets 4 times 4, which is 16. Now you do it. So that is 5 times 3, which is 15. Okay? You have to add, okay? After multiplying, you write one after the other. Now you split only one pile into 2 different ones. So C gets 3 times 1, which is 3. And he gets 3 times 2, which is 6. Now you go. C gets 2 times 2, which is 4. So he gets 2 times 1, which is 2. Yeah, go ahead. So C gets 1 times 1, which is 1. You do what you like. He gets 2 times 1, which is 2. Yeah. Now, C gets 2 times 1. You? 1 times 1. Okay. C gets again 1 times 1. You match it. You have no choice. Yeah. 1 times 1. Right. You have also no choice at this point. 1 times 1. Then yours last step would be separating that out. 1 times 1. Now, Mr. Scorer, what scores did? What? Let's see. So this is my political game. Okay, I first showed you how to play it. That came out to be 28. I did it in some random way. You did it by thinking hard, sweating, and so on and so forth. You are also perhaps very concerned that you might lose or whatever. But both of you ended up getting 28. What is the secret? Now, my political message is that I would like to live in a world where nobody will beat anybody else. There will be no winning and losing. Part of the reason we are messed up, is that we are always trying to think somebody will win. I'll get ahead of someone. I'll be behind somebody. This game, and I'll show you if I get a chance, this game shows you that as far as this is concerned, there is no winning losing. You can do whatever you like. This can be a pile of 1 million such things, and you can.
But we will end up with the same sum.
You will end up with the same sum. What is that sum? Oh, 28 for 8. That we have seen. Huh? Sum of natural numbers equal to the blocks. Yeah. So n times n minus 1 divided by 2. Yeah. Okay. That's very good. Now, all right. So this is this. Let me try something. Yeah, you can sit down now. I hope all of you will agree. I am not doing this many more times because there is math, right? So it cannot go wrong. I might mess up, but the game will not go wrong. You will always only get 28. Unless the scoring is not right, or unless something or the other is not done right, but otherwise it will always be 28 with 8 blocks. By the way, all of you who look at internet and stuff, you can see that there is a very nice lecture in MIT. That's from where I have borrowed this. There is Computer Science 101 or something. Some very boring looking guy walks in to to give a lecture. And in the beginning, I think, oh, this can be very interesting. Very surprisingly, behind the boring looking whatever manner that he has, a very interesting lecture. He walks in with much bigger blocks, wooden blocks, and he starts making stories. He has also brought, unfortunately I did not, he has brought what in America they call candies. He has 2 big bags full of candies. And then he says, let me make some teams. In the US there are these tutors and then there are the students. Now the tutors are not very much liked by the students because they kind of do the grading, this, that, and not everybody is happy with the tutors. So he makes 2 teams, one consisting of the tutors, the other students, and he kind of sort of keeps telling them, oh, you can do better, you can do this, you can do that, and he is playing this game. And in the end, of course, and then he says that I'll give whoever wins gets this candy bag and so on and so forth. All of this drama he does, and finally in the end nobody wins, okay. So it's a very interesting lecture. That's not the only thing he does in that lecture. He does many other things. I don't know if I should have brought it with me now, but okay, I forgot to add that. There is another thing which is very interesting. Okay, maybe that's for another day. When I become a professional, then I'll invite you to, yeah. Okay, let me try something else that may or may not go very well. And for this also I might need a volunteer. Okay, let's see. This I was trying last night. Let me see if I can pull it off. Yeah. All right, so we are now, okay. All right, I like to be in the same level, but what to do? So, I'll do 2 things one after the other. Now, I forget the name of this very, very wonderful Japanese mathematician. He has tons of things on the internet. Tosida or something, I forget. So this is an illustration. You can see this is a paper. This is cut in a certain way. Okay, I hope I don't tear it off. Then I cannot sew. Already I tore it off a little bit. So this has 2 surfaces. You see, if I hold this paper like this, I cannot go below because my hand is going to be obstructed by this wall. Similarly, if I am holding the paper from below, I cannot come up, right? Because if I hold it like this, to bring this paper up with my hand, I need to go past this barrier. Cannot do that, right? Now I need a volunteer. If hopefully, if we do it carefully, I'll show you something. Namely that, indeed, while you are holding this below like this, I'll be able to pull it off so that this comes past this obstruction. Can you imagine how it can be done? All right, come. One of you come and hold this. Yeah. Hold it like this. No. Just this part. Okay. Just hold that part. Let's see if I can do it. But last night I was, so now this is actually, what happened? You are holding it from below, right? It has come up now without you are crossing that barrier, right? So, the reason I wanted to do this is there is something. So now let me follow that up with, no, you can go back now. That's the only thing I wanted to show. There is now something that you would have noticed or seen anyway, but what happened to my little strip? Oh, I see, I have put it here. This is the trouble of not being, I don't have enough practice, so let's see. This is, please remember what happened here. What did happen here? We said that there is a below and there is a above, right? And it was separated by this middle thing, and that is why you could not go from one side to the other. Remember the word side, top or bottom or side. You are not able to go from one side to the other side. This is a property of that particular object that I showed you. In mathematics, often we like to say that this thing is the same as the other thing, okay? We make our life simpler by simply defining what one might call an equivalence class or something like that. So this bunch of things is the same as that bunch of things. So you have seen one object which is sort of has a top and bottom, and you cannot go from one side to the other. Now let's see if I can show you that in an equivalent way. This many of you of course would have seen. In fact, when we used to do that, what is it called, our Founders Day or something, a bunch of things like this one used to do. So, yeah, this many of you, as I said, with my apologies, you would have seen. But I am not going to stop there. I am going to say why or how. I knew that all of you would now make a face at me saying, oh, why wasting our time, we know all this and so on. So we'll go a little beyond that. Okay, so what all of you know is this, but for those couple of people who may not know, let me do it anyway. No, it's okay. Yeah. This is where, yeah. No, that's okay. Yeah, this now goes.
You will cut it.
Yeah. Right, now I will cut it. Oh, but yeah.
You have only one, right?
Yeah.
You could do it for 2 or 3.
Yeah, I could do it for 2 or 3, but that's not what I'm going to do, because of course that also is fun. So now you see my comparison is with that surface. The point is you could here go from here and here and here and come. Starting from the top, if I had a colored, actually that's why I had that pen. And I also have another pen. So, so if you look at this is on top right now, right? Generally speaking, if you have a top, you cannot go to the bottom without crossing the edge. That's the whole point, right? But now if I continue, I am not crossing any edge, right? Because I am drawing only on the surface. Now you see, the whole point is, I showed you this as the top and this is the bottom, but I have come from the top to the bottom without having to cross the edge. But there I demonstrated to you how by reversing the orientation, when I'll maybe talk about that a little bit more afterwards, but let me, I want to do something, I want to stop. No, that's okay now. Actually, by the way, talking about magic and such, when I was a kid, there was a magic show that I went to, and you won't believe, there was a professional magician who came, and his first trick was this, except the ring that he had was so big, it was perhaps 20 feet or something. So you can't notice the twist that I made. You know, if it is a much bigger ring, then you won't be able to. Actually, before I do that, this is falling apart. So it's better. No, maybe it's okay. No, that's how it should be. It's okay. So he did that magic trick, standing on a stage, and what I'm saying is now I can also do it. I was very impressed. So now you see this thing is now in a single piece. Why is it becoming a single piece? That I can show you again. If I were to, this is what one does in topology. So no, this I just want to, yeah, okay, no, that I need the pen. So you can see that, okay, I'll go up again. See, what you are doing, if you follow through this line, and if it was like this, just a ring, it will become two parts, right? There is no question about that. What in topology one calls twisting is that you are doing this. Now, okay, this I didn't take a big enough whatever, but now you imagine where the line is going. You are sort of, instead of this edge matching with that edge, because of which you get the triviality of this falling apart into two parts. Now you do this, so this part of the edge is stuck here. This part of the edge is stuck here. So when you are cutting, you are coming from behind, and if it is stuck here, then it will, instead of falling apart, it will become a single piece. That is how you more or less define what one might call a one-sided surface. Actually, there is something much more interesting. I should have thought of it and brought with me, but anyway, okay. I'm just trying to remember all the little things that one could do. But as somebody said, it's not interesting enough to do just this. Let us do something more. And then I will stop more or less. Let me see. Can you sort of hold? Let's see. I want to take 4 pieces like this.
You have sufficient.
You mean paper? Yeah. I think I'll last 2 more things like this. And again, I want to. So one of the things I wanted to say with that Mobius strip thing is that where you will find this on the internet, particularly this one by this Japanese mathematician Takeda or something, I forget the name. After he shows this, he demonstrates that you can go from top to the bottom without crossing an edge. That's exactly the property of the Mobius strip. You can go from top to the bottom without crossing. That's exactly what is equivalence in mathematics is all about. Here is a surface where you can go from top to the bottom without crossing the edge. This piece of paper, which looks very different, right? This is nothing like the Mobius strip. But here also you can go from one side to the other without crossing an edge. That's what makes this equivalent to the Mobius strip. And this is said by not an ordinary useless mathematician like me, but by some great man, namely Jim Simons. Jim Simons is not a great man because he has done, of course he has done great mathematics, but not only because of that, in spite of being a mathematician, he is among the, perhaps he is as well off as Bill Gates or even more. When I was in Stony Brook as a PhD student, he had just left. Actually, Jim Simons. How many of you have heard of Jim Simons? Very good. Okay. Jim Simons is a mathematician who gave up doing mathematics and became a gambler, if you like, for lack of a better word. At that time, there was no real math theories or, hey, why don't you sit down? Yeah. When I went to do my PhD, Jim Simons, who used to be the chairman of the Stony Brook Math Department, had just left. And like I would say here, you know, people sort of run a pan shop or something like that, chota cabin on the roadside, and then you sell pans or stuff like that. There was a railway line, you know, defining the Stony Brook campus, railway line going from Stony Brook to Port Jefferson. And across the railway line, Mr. Simons had set up a shop. One chota cabin, one table and so on. And he called it in those days Money Matrix. The name of his shop was Money Matrix. Simons himself was responsible in bringing a lot of good mathematicians to the Stony Brook Math Department. When he got this idea that you can make money using math, he decided to steal all the good mathematicians he had brought to the math department. So there are many good people who actually gave up doing mathematics and chose to work with Jim Simons. In fact, to tell you a little story, there's a very, you know, very distinguished complex analysis guy who used to teach us. 8 or 10 years ago, I was looking for something. I said, oh, this guy must have done something along those lines, whatever question that I was thinking of. Then I started looking him up. Then I find that, you know, over the last 20 odd years, he has not written anything. I said, what happened to this very good mathematician? Where did he disappear? And I start wandering around, asking people. Turns out he joined Jim Simons. And then, of course, he became a second-hand man of Jim Simons and made tons of money and so on and so forth. So Jim Simons, who is a topologist, differential geometer, is a very interesting character. Coming back to my story, when Mr. Takeda, or, you know, I'm sorry that I can't remember the name correctly, this Japanese mathematician, finishes doing this, there is a little snippet from Jim Simons that appears. And then he comments, as a result, this is equivalent to the Mobius strip. And if I were to quote him directly, he then says, can you build buildings with this Mobius strip? The answer is no, but who cares? Something of that kind is how he puts it. Now let me finish by doing two more things. Let's see how this goes. I hope I can. Yeah, no, I just need to stick. Yeah, we'll just, yeah.
I'm just holding.
Yeah, let's just, yeah. Let's just stick it like that. That's enough, I think. Now, no, I need to stick it like this also. So how do I do it? Yeah, I am generally a very miserly guy with everything. So, yeah, okay. And then let's take this fellow and stick it like that. Yeah. Yeah, no, that's fine.
Okay.
Yeah. But then I'll do something else, and then that will be the end of the magic part of it. Then I'll try to bore you with something or the other. Okay, maybe, maybe
some more is required, right?
Yeah, right. Yeah, it's better to stick it.
Yeah. Or put a cross in that way. Then
No, now it's done.
Yeah.
Okay. No,
Shall I
here.
put one
Yeah,
there?
right.
Yes.
Okay. Now let's see. Who wants to hazard a guess? What do you think will happen? I want to cut this in the middle, like I did with the Mobius strip. Anybody has any idea what will come out of this? That's right. What perimeter? Provided I do it right. If I don't do it right, of course, nothing will come out. Something happened. This. No, this is this.
You need a,
No,
you need
this
some
should,
more.
no, this should have been, this is like this is like this. It's done.
Okay. Should I remove
Yeah,
this?
yeah. So that
It
if you,
doesn't much
yeah,
interference.
right. If you want to see, then this is, if that is what you meant by perimeter, that's exact. Yeah.
Yeah.
I have a better one. I'm going to finish with a last one, okay? Now, yeah, this is now no good, so let's forget it. Now let's do one other thing. Now, how do I do it?
Double fold.
Yeah, two Mobius guys. But how do
You
I?
need a little bigger, probably.
Yeah, probably it's better to have a bit bigger. So let's forget that. And then this, I promise you, you wouldn't have guessed. I mean, unless of course you have seen it before. No, that's okay. Right. So, what we do is to let's put this thing here so that it doesn't fly off. And let us,
You want to put a cross
yeah,
like this,
yeah, that's right. I want to put a cross like that with more or less, yeah, maybe, yeah. This, yeah, put it in the middle.
right?
Right, yeah. Now,
One more?
yeah,
This
perhaps
side?
you, no, just put maybe like that or something, yeah. I don't know, I mean, sometimes it seems to come off, so it's better to.
I'll be just not on table.
Okay.
I mean, that will,
That is okay. We can
pull it
manage
up.
it.
Yeah.
We can pull it out.
right,
It's not an issue.
yeah.
We can just cut a little bit here and there.
So are you, all of you, getting bored now? It takes a bit of a preparation. I could have come prepared, but you know, these things will lose shape. It's hard to bring it. Besides, I am sure all of you enjoy my feeling completely nervous and, you know, I don't know what's going to happen, right? So, yeah, fine. So, what we do now is to make it into a Mobius guy. So, let's see what will happen. Is this the Mobius fellow? Yeah, right. Now let us sort of strip it around. Yeah.
Just hold it and
Yeah.
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 This is one. The one I
Yeah.
think you need. One
Yeah,
more.
but let's just put a little bit. Last time there was a problem because of that, so let's put.
Some more.
Yeah.
Yeah.
Right. And now I take. So this is the one, and now I take this, and this is again Mobius, right? Yeah.
Uh,
Yeah.
Slightly less came up here. I
No,
will
no,
put
we'll
in
put it
other
in the
side.
back. Yeah.
Yeah.
Good. Yeah. You can even hold it. All right. So I am ready for the last one. And then I'll try to, if you are still patient, I'll try to explain some of the tricks that we have seen. Okay, let's see what happens with this one. It doesn't happen the way I expected. It's not the mistake of, it's my mistake rather than what is supposed to happen. The math cannot go wrong, okay? So now what happened? Let me go. You had an idea last time. Now what do you think will happen? Same. Okay, let's see. You mean the fact that I have a Mobius stuck on both sides makes no difference? Become a normal stuff. Okay. Let's see. Now I don't want to show you what exactly is happening. If I have done it right, okay. Actually, I should have done it with a smaller size. It should look like two hearts, one inside the other. It perhaps didn't come out as well as it should have. Yeah, see that kind of corner, yeah. Yeah, it should have, I mean, you can look up the internet and see how nicely it comes out. I made it, yeah, I made it a little too big. That's why I mean, the strip size should have been smaller. Now let's look at a couple of things. Let's see, 12:30. Okay. There is one last thing I want to do in terms of just games before I go on. This, can you sort of just go on with, yeah. Please, yeah. Yeah, this. Yeah, just go over the, you can do it. Okay, so now you can do it by yourself is what I'm saying. So, here I have a polynomial and it has coefficients between 0 and 2. Okay. This is an arbitrary polynomial whose coefficients are between 0, 1, 2. Alright. determine all the coefficients. That means, like the games we have been playing, you think of a polynomial. I don't put any constraint on the degree. This polynomial could be a polynomial of degree 117, okay? Only thing I say is that its coefficients are either 0, 1 or 2, okay? Now here is the challenge. Can you just push one more time? That's right. You can ask for the value of the polynomial, which means that you have thought of the polynomial of degree 117, coefficients 0, 1, 2. Now do me the favor of telling me what is the sum of this polynomial evaluated at 3. Value of the polynomial evaluated at 3. Now imagine, because you have thought of a polynomial of degree 117, I have to tell you how many coefficients. I will be able to guess your polynomial just by knowing this one value. How many coefficients I have to tell you? I have to tell you 117 coefficients. But these 117 coefficients I will be able to tell you by just knowing one value of the polynomial. Can you guess how or why? Yeah? What? No, degree of the polynomial is a variable. It doesn't matter. I don't say that the degree of polynomial is this or that. You think of a polynomial, any polynomial that you like. It's only the value of the polynomial at 3. Then I will be able to tell you what the polynomial is. Now please remember, one of the things when we teach complex analysis, I don't know about we, but I like to say that analytic functions or whatever it is are sort of really polynomials which refuse to stop. Polynomials have a degree. If you look at analytic functions, they don't have a degree. Well, what is the big difference? Polynomials are completely determined by their coefficients, right? So the moment you know coefficients of a polynomial, you know the whole polynomial. But imagine if you had an arbitrary function, there is no such thing. You cannot determine an arbitrary function by knowing only a finite number of values. Polynomials you know because they have finite, there is a factorization in terms of zeros and so on and so forth. Anyway, without making too much of a fuss, let me ask you a simpler question, and I am pretty sure you will be able to answer that. And in that case, I will go back to the question with the 3. What if I were to tell you that the coefficients of the polynomial are 0, 1, 2, 3, up to 9. Suppose the coefficients of the polynomial, this is an arbitrary polynomial, completely arbitrary. The only constraint I put is that the coefficients are between 0 to 9, 0, 1, 2, up to 9. Now you design a question that can be asked so that by knowing the answer to that one question, you will be able to tell what is the polynomial. How many of you can think of the question? What is the question you will ask? X equal to 1 will give you the sum of the coefficients. It will not tell you what all the coefficients are. Evaluate the polynomial at 10. Evaluate the polynomial at 10. So let me do it on the board. Finally, after all, as somebody practicing math, one should go to the board at least once. So you have a polynomial a0 right. Now each of the ak's are between, okay. Now suppose we call this p of x and I ask you, you tell me P of 10 is some number. What is that number? It's A0 plus A1 times 10 plus A2 times 10 square plus An times 10 to the power n. Now, as you know, if I know this number, then I know the decimal expansion of the number from which I pick up the coefficient. Somebody tells you instead of this, then what would you do? Oh, lesser or equal to 3, I said. Yeah, okay. It was my slide is up to lesser or equal to 2 rather than. Yeah, 4 is right. I mean, if I were to make it 3, 4 is right. But now I can make it a little bit more complicated by saying that if I don't know that my coefficients are between such and such, I simply say the coefficients AK belongs to natural numbers union 0. Suppose this is all I know. I still have an arbitrary polynomial. Its degree is free. Okay? N is arbitrary. Degree of P is equal to N is arbitrary. Coefficients are arbitrary. Now I want you to find the polynomial by knowing some very, very small things. Okay? So first of all, you cannot do it by asking one question. You have to ask 2 questions. Let me give you that as a hint. Suppose you are allowed to ask 2 questions, then how do you find the polynomial? Well, since it's getting late in the day, what you said before is actually right. In other words, now suppose you evaluate the polynomial at 1. If you evaluate the polynomial at 1, you know that the sum of the coefficients is such and such. In other words, now I can say AK is lesser or equal to P of 1, bigger or equal to 0. So I evaluate the polynomial P at P1 plus 1. And then I get expansion according to. So, yeah, was there a question? No conjugative. It can be any number. Yeah. Because you are just looking, see, if you go back to this expansion here, these A's, here can be any number between 0 to 9. They don't have to be conjugative or anything like that. Okay? Actually from here, I talk about this as a ternary expansion and go into talking about what is called Cantor set and stuff like that from looking at this polynomial. But now let me show you just one more game, and then you can sort of go back to the folder.
No, go back to
folder, yeah, and now go to that 27 cards. Also, because there isn't a lot of time, I am now conflicted. What do I explain? It should be index HTML. Okay, let's try to play again just with one volunteer. Let me show you. I showed you a card trick with 21 cards. Now here is a variation, and this will explain how this trick or such tricks are done in general. If you like, it can be stated or explained in terms of modular arithmetic and this, that and the other, that I am not going to go into. But let us pictorially understand how any such trick is done. So let us say you, any volunteer, can you think of a card and then tell me which row it is in? Anyone? Okay. Third row. Okay, can you please click on row 3? Yeah, row 3. Now? Again third. Okay, click on 3. First. Okay, click on first. Right? All right, this can be repeated as many times as you want. But why? There is something called secret HTML. Go to secret HTML. There should, go to secret HTML. All right. Now let us, for fun, I don't need a volunteer for this. I just want to explain how this is done. Actually, there used to be a better colorful thing. Let us say we pick, what is this called? 2 of spade or something? Club. Yeah, right. Yeah, just like math, I get confused with all kinds of. Yeah, 2 of club. Let us say we have picked or thought of 2 of club. So 2 of club in the second row. Now please click on second row. Now you see what has happened is that, did you, okay, no, that's fine. So 2 of club, if you look at this, it is on this second row, right? This second row has 9 cards. They are grouped into 3 colors. This color, that color. When you click this can be done, that's what I was doing, shuffling the cards. When you shuffle the cards, what you are doing is you are putting this middle row right in the middle of those 2, top and the bottom row. What then happens is that this set of 9 cards gets divided between the 3 rows again. So that second row now appears as 2, 6, 5, whatever this is, queen 2 and king and 9, 7, 9 or something, all right. Now we know that this 2 of club is still in the middle row, so please click on the middle row. Okay, so now this thing that was picked from middle row, because in middle row only those 3 things are relevant, that gets divided into these 3 rows, but now since you have 3 things to divide, what happens? It gets distributed as 1, 1, 1. Now if you tell me the card that you thought of is again in the middle row, please click the middle row now, one last time. Okay. So, so what happens is, as I said, in that 21 cards, 27 cards, this, that, and the other, there is a lot of, as I said, you can sort of, the whole idea is that, you can do it. I mean, you just have to be careful. You have to work out. Actually, there are many sophisticated versions of this that I did not go into, but you can do it in a very, I mean, as I said, when I do it for money, and I am actually doing it, and I don't have a job as a mathematician anymore, then I will be selling tickets and then doing things, then I will do the more sophisticated version. This is, so, okay, so that's the card trick. We have looked at some of these. Oh, I wanted to show you that this dominoes that came out as the same, it's an induction argument, okay? If you write down what is happening, you do the induction argument, you have to do it a bit carefully. And as I said, that MIT lecture actually has it. I have it also, if I had, no, it's 12:52, so I don't want to push my luck. But the dominoes are a inductive argument. You can say you are starting with these 8 things there. You don't have to worry about two players. You just look at one pile and you say that no matter how you split it, the answer will be always summation 1 to n minus 1. Yeah, right. N times n minus 1 divided by 2. That's because it comes out as the, that comes from an induction argument. The first card trick, what we had, if you look at the way this is done, I can go up to any set of numbers, but the way it is done, okay, maybe for one last time I'll go up here. If you look at, actually I could have done it in a more interesting way. these first two rows, if you look at, the number 1 is the critical piece here. This says that if your number is on these things, in its binary expansion, 1 occurs. Okay? Every number between 1 to 31 that has a 1 in its binary expansion is written here. So the moment you put a tick mark here, I know that you have thought of a number whose binary expansion has an 1. Similarly here, if you pick the number from here, I know that in the binary expansion of the number that you have thought of, there has to be a 2. Same here. Every number which has 4 in its binary expansion is put here. Every number which has 8 in its binary expansion is put here. Every number which has 16 in its binary expansion is put here. So the moment you pick this row or that row or whatever, I know exactly which numbers occur in the binary expansion of the number that you have thought of. So all I have to do is add them up. Okay? What? You are thinking of a number between 1 to 31, right? So suppose you are thinking of 19. Then you are looking at 16 plus 2 plus 1.
Also, even powers.
By binary expansion, that's what I mean. That's why, so since we are late in the day, I am not trying to explain it in the 1, 2, 4, 8 and 16. These are the powers of 2. Every number between 1 to 31 has a unique expansion as a sum with coefficients 0 or 1 in powers of 2. And you have told me, knowingly or unknowingly, exactly which powers of 2 occur in the number that you have thought of. And then it's a trivial matter, to add them up. Even I can do that. I can't do a whole lot of serious mathematics, but I can still add numbers. 3 and 2, I will come up with 5. Okay? Alright, so that's it for today. Tomorrow I will try to perhaps do something else. Let's see. Yeah, thank you. Yeah. No, but I must thank all of you because, as I said, this is my stepping stone to becoming somebody who can choose an alternative career. Okay? No, but for the next lecture, I will not get down. I will sort of.
So we'll do some more arrangements
Right.
so that it's a better.
Sure. Yeah.
So there is a question here.
Yeah. Well, what happened to that? It's defined by the idea that whatever the surface is, I can go from the top to the bottom without crossing the edge. If that you take as the definition of the Mobius strip, what I am saying is that in this surface, I showed you if somebody is holding this like this is the top. By doing what I did over there, like this, and pulling that thing through, this comes below. So I am able to go from the top to the bottom without crossing the edge. And that I take to be the definition of the Mobius strip. Okay. No, this is not with the line. This is only with respect to this property. I am saying this property of this surface is exactly the same as the same property of the Mobius strip. Now, if you want to take it as a definition and define that as equivalence, then to that extent this is equivalent to that.
Any other questions?
Yeah. Yeah, that's what Simon Sackville said. It will not be a very useful building. But yeah, apparently, according to equivalence, I mean, typically in an equivalence class, there are lots and lots of, I mean, an equivalence class is rare in a single program. Here, of course, I am trying to say, in this equivalence class, I have told you that there are two things. But, you know, I mean, I haven't thought about it, but I'm pretty sure you are defining only a homeomorphism. If I'm not very good at thinking on my feet, but if you think about it, equivalence here means homeomorphism of a topological space. You know, homeomorphism is just a continuous map that is inverted, you can go on. I mean, this person who did it, he actually said that if it was a, for example, a rubber surface, rather than being a paper, which is solid, I can, even when I am holding this below, if this was a rubberized thing, I can pull it and then lift this from below. So, but this is paper, and so, you know, you cannot do that too long. Okay. Yeah.
Any other questions?
Is there any other questions? Are there any other questions? If not, let's thank the speaker.
Thank you. Oh, I forgot to tell you something about the commuters, but huh? Yeah. The whole thing about math talks is that one tries to say